Hello and welcome to our pre-flight on Momentum Collisions, a journey through crashing thingies. My name is Amit Lohitsa and this is my partner Robert Kerner. Say hi, Robert.
Hi, Robert.
Bobby Kerner again. So, before we start, let's talk about a few things. The viewer here should know
Newton's three laws.
1, 2, and 3, folks.
Kinematics.
Where things move.
Moving things are always interesting. And energy.
Where, the thing that causes things to go thing. Alright.
Stuffs.
Move
stuffs.
Energy is work, and what causes, what? Work? Stuff? Yeah. Alright.
So through this video, what you should learn is
momentum, impulse, and collisions. You know a lot about collisions already. You see them in daily life. What happens when you clap your hands together or a car crashes, as you see here. This man's like, what? This man's like, ah! But anyway, you're going to learn a little bit more of a physics explanation on what is happening here in this very picture.
Okay. But after this, once you are finally done with your momentum lesson, you will be learning later on about oscillations,
Spinny thingies.
and simple harmonic motions,
Spinny thingies.
swinging thingies.
Swinging thingies. Yeah, quite a concept.
So let's start with the types of collisions.
So here we've got our elastic, inelastic, and totally inelastic collisions. There are differences between these three, believe it or not. So elastic collisions are when objects bounce off of one another, and then the kinetic energy is conserved. So they bounce off of each other, and an example of this would be pool balls hitting each other. So when the two balls collide, they bounce off of each other, kinetic energy is conserved. We could analyze that specific situation with a fine microscope, but you get the idea. It's when kinetic energy is conserved. Big idea. Now, inelastic collisions are when you have some energy being converted to other forms, like heat, sound, and light. Okay. Settle down here, Sparky. It's okay. Alright. Pardon that, folks. That is my dog named Sparky. Anyway. So, again, inelastic collisions. Some energy is converted to other forms, like heat, sound, and light. So, the example here is when you got a car crash. The two cars will crash into each other, and some energy will be converted in the process to heat, sound, light, etc., and others will be lost due to kinetic energy because, kinetic energy, again, will have mv squared, but the velocity is rapidly changing, etc. So, now the most extreme form of an inelastic collision is totally inelastic. And that is similar to inelastic except for the fact that all totally inelastic collisions will stick together because of the maximum loss of kinetic energy. There's a maximum loss here, making it the most severe type of inelastic collision. And again, that would be a car crash. Same example. So now, with conservation and collisions, we can talk about the law of conservation of energy and the law of conservation of momentum. And we'll explain the equations behind those in a minute, but the idea is that the kinetic energy in equals the kinetic energy out, the momentum in equals the momentum out. It's the same process here, but momentum is always conserved. Momentum is always conserved. That is what you need to know here.
Is momentum conserved?
What? Yes, it is! How did you know? Okay, so in an inelastic, totally inelastic, and elastic collision, momentum is conserved. The same goes for total energy, but with mechanical energy, the only time it is conserved is in inelastic. Remember, we talked about that. Yeah, exactly. Alright, and it's not conserved in inelastic or totally inelastic. Okay, next. No collision fits perfectly into these categories in nature. I'll say it a little bit quicker here. No collision fits perfectly into these categories in nature. You could analyze these with a fine microscope, but, nothing fits perfectly. Alright. So, let's get a little bit graphical here. So, you've got two blocks here on the left side before. They're heading towards each other. Afterwards, they're heading away from each other. This is just one scenario of an elastic collision. They have bounced off of each other, and the energy is conserved. Momentum in is equal to mv, and the momentum out. Kinetic energy in, 1/2 mv squared, is equal to the kinetic energy out. And, a good example of this is the Newton balls, the thing that teachers keep on their desks. So, when you lift up one ball and it hits the next one in the series of Newton balls, the other ball will come out, and that's because the momentum in is equal to the momentum out. The energy and the momentum is conserved. The law of conservation of momentum, the law of conservation of energy, folks. That is what this is. Elastic collision. Energy is conserved. So is momentum. Okay. So, in an elastic collision, before and after. Before, these two objects are going to be heading in the same direction. This is, again, just a scenario. These blocks are going to be heading in the same direction. The first block is going to hit the second one, and they're going to continue forward as one system. So, in this scenario, not all of the energy is, going to go as kinetic energy. Some is lost to heat, sound, light, etc., but it's going to keep moving forward. So, in the next picture here on the right, we've got two masses, m and 2m. M is moving at a velocity of v1. M is moving at a velocity of v1 over to 2m. M is going to hit the other one, and they're going to move forward as one system at a new velocity. So that's the idea of an inelastic collision. Some of the energy is conserved, and some of it is, converted over to other forms. Now, we have another scenario, which is a totally inelastic collision, which is, again, where the maximum amount of kinetic energy is lost because it's the most severe collision, or severe inelastic collision. And again, the same thing is going to happen here with the masses, but it's just a matter of how the energy is transferred or lost, etc.
Okay, now let's talk about equations. So the equation associated with momentum is P equals mv, where P represents momentum, m equals mass, v equals velocity. And what we already talked about before is conservation of momentum. So conservation of momentum, everything that goes in goes out. The P before equals P after. Momentum before equals momentum after. It's really straightforward. Everything stays there within a system. Not necessarily an object, but within the system. And so what you see right next to that is mv1 plus mv2 equals mv1 plus mv2. And that essentially means that the addition of all the objects, the momentum of all the objects before, equals the addition of all the momentum of objects afterwards. So the units for momentum are Newton seconds, or kilograms times meter per second. So impulse. Impulse is another new thing for you now. Impulse is represented by J, and J is the change in momentum. And since mass is almost always a constant in most problems, it's basically the same thing as m times delta v, or mass times the change in velocity. So the units for this are also newtons times seconds, or kilograms times meters per second. And the most important thing about impulse is that it depends on the direction. So if you look in the upper right hand corner with this picture, you'll see if the object is coming towards a wall and it hits a wall, it starts with a given mv, or momentum, and then it goes out at a different momentum. The impulse is going to be a change in that, so the two negatives cancel out, but you are left with 2 mv, which is the same thing as twice the original momentum. So in an elastic collision, like I just described, you will always have this double the original momentum as the impulse. For an inelastic collision, the impulse must equal the original momentum, because the final velocity will always be 0. So you're going to end up with the exact same momentum in the end. And another really important thing to mention about impulse is that it does not vary based on the elasticity of the object. This only varies the transfer of energy, and this being the elasticity of the object. So if you have a really bouncy ball, it's not going to change how the impulse is found. It's only going to change how the energy transfers. Continuing on impulse, impulse is related to force through the integral of force with relationship to time. So essentially you end up with the same thing of m times delta v, or the change in velocity, but the change in force with relationship to time is always the impulse, And right here, I have a little, I have an explanation or a proof for how this happens. It's not very detailed, but this is the same thing. In other words, impulse is the change in force over time. So as you can see in this lower right-hand corner with the this graph, the area under the force and time graphs leaves how you leaves you with the impulse. So an example of impulse is friction caused over a given amount of time. It's not the friction given over a certain amount of distance. That's different. That is work. This is impulse. It's the amount of friction over time. It's really important. So it's also important to notice impulse is the average force over a changing number of time. So if you extend the time of collision or reduce the average impact on the force, it will affect the impulse in the end. So for a given change in momentum, the impulse stays constant because the time and the force change with regard to one another. So thank you for watching our pre-flight.
Have a great one, folks. Woo!